Hello everyone, I am Nicolay Marie Calor Villar and I am the first presenter of our group. Our study is entitled Object Detection for Quality Produce, YOLO-based classification of fresh and rotten vegetables. So first, let us now proceed to the introduction. So the world's population is expected to grow a lot, reaching 9.7 billion by 2050. To feed everyone, we need to produce more food means more vegetables. Making sure our food is safe and good quality is really important. So that is why we need to find ways to check how fresh the food is. But the farming industry in the Philippines is not as efficient and productive as it should be compared to other industries. To fix this, we should use new technologies like blockchain, IoT, and AI to make farming more sustainable. However, the challenges persist in leveraging big data analysis in agriculture in the Philippines due to governance and standardization issues, lack of human resources, and inadequate infrastructure. Luckily, a new computer vision model called YOLO version 8, or also called You Only Look Once version 8, can help us check the quality of farm produce in a better way. Now, the problem or challenge lies on how to establish a reliable system to assess the freshness of vegetables, crucial for both the fresh goods trading sector and individual consumers. Therefore, our study aims to explore the application of the latest YOLO version 8 model in computer vision for automated quality evaluation in agriculture. This research aligns with the broader objectives of promoting sustainable practices, reducing waste, and ensuring a consistent supply of safe and high-quality food products for a growing population. Additionally, our study's potential extension to sensor technology could significantly contribute to data collection in the agricultural sector, facilitating its development. Now, let us now proceed to related studies and literature. So, the use of computer vision, especially through a method called object detection, has brought about a big change in how we assess the quality of agricultural products. This shift in technology, represented by YOLO, or You Only Look Once, has changed how we tell the difference between fresh and spoiled vegetables. This not only ensures safer food and less waste, but also makes the evaluation process much quicker. YOLO stands out because it can process information in real time and is very accurate at judging the quality of produce. Moving from the traditional way of checking things manually to using YOLO-based automated systems not only speeds up the process, but also saves a lot of money on labor and helps in making better decisions in the entire farming supply chain. Even though YOLO has clear benefits in terms of efficiency and accuracy, there are still challenges like differences in lighting, how the produce looks, and different stages of decay. People are working to improve YOLO by refining the information it uses and adjusting its structure. The goal is to make YOLO even better, creating systems that are more reliable and flexible for accurately assessing the quality of agricultural products. That is all. Let us now proceed to the next reporter.
Greetings to you, Ma'am Ivy, and to my classmates who are watching this video right now. I am Faith Elijah Emibano, and I will be discussing the methodology part of our research paper. So this section is divided into three parts: data understanding, data preparation, and model selection. So in data understanding, it basically contains details on where we collected the data, the details on the original data set, and then the second section, data preparation, contains details on how we prepare the data for training. And then lastly, model selection. We will discuss here the architecture of the model that we have selected, or the algorithm that we have selected in order to create the model, and also the how the training process went, or how we perform the training. So before we start, I would like to add also that in order to realize our goal, we mainly utilize RoboFlow platform. So, RoboFlow is an open source platform um, where it provides frameworks for computer vision related tasks such as image classification, object detection, image segmentation, and other computer vision related tasks. So in RoboFlow, you can store the data set there, perform annotation there, and also train the model there, and also deploy the model there. So without further ado, let's dive into the details of the methodology. So the dataset was downloaded from Kaggle, which is a famous a pool of uh, data, dataset source. So we downloaded the dataset there. We downloaded the dataset from the Kaggle, which was entitled Fruits and Vegetables Dataset. So the dataset was uploaded there by Mukridin Mukridinov and his associates, as they use this dataset in their study or in their research, improved classification approach for fruits and vegetables, freshness based on deep learning. So in this study, they compared YOLOv8 and YOLOv8 performance in classifying the freshness of fruits and vegetables. So YOLOv8 and YOLOv8 are, of course, older version of YOLOv8, and since they're older version, of course, YOLOv8 outperforms these older versions, since YOLOv8 is an improved version of YOLO. So uh, it just know just sharing that in their study they achieved around just 50% of um precise value on preciseness of the uh model they have made, but considering during that time YOLO v4, so considering that was pretty high um for an object detection algorithm, that is considerable decent performance for an object detection algorithm. So I have here the table for the summary of the number of images in the dataset. So since we will be using vegetables only, so we ignore the fruits, vegetables, and the fruits dataset and only use the vegetable dataset. So in the vegetable, there are bell pepper, carrots, cucumber, potato, and tomato. So there are 5 vegetables in total, and since we have fresh and rotten for each vegetable, so there are a total of 10 classes in our study. So we have 10 classes, and each classes have around 600 images, 600 approximately 600 images um, in each class. And here's a sample. Below here is a sample of the images. We have fresh carrots, and below fresh carrots is the corresponding rotten images of the vegetable. So next is the data preparation. So the images the images are unannotated, so they have no labels when we downloaded them from the Kaggle, and so we annotated the data set manually, all those uh, images, and then we tried to balance the data set. In object detection, it is unlike image classification. So, image classification, it is important. In image classification, it is important for the number of images to be balanced. However, in object detection, it is important that the number of annotation boxes are balanced, or the number of annotation boxes matters in terms of a balanced data set. Then we resize the images since the original data set has a size of 640 by 640 pixels, and that size is um, a very large size for image in our current computational resource. So it requires a lot of training time, and the machine in the RoboFlow uh, says that 640 by 640 is too big, so it cannot compute. So we downsized it to 240 by 240 pixels, and then we augmented the images. So we perform augmentation in order to increase the number of the number of annotation boxes, since according to Ultralytics, which is a famous, which is a popular intuitive AI platform for training, in machine learning, for training, um, yeah, for training in machine learning. So that they said there that in order for the YOLO V8 to perform well, your dataset must have over 1,500 images or yeah, instances. So we augmented the images, and the table here contains the number of annotation boxes in each class. So as you can see, the number of annotation boxes in each class is around 1,700. So we tried to balance uh, the annotation boxes in each class. And we have here sample images of the um, have here sample images of the augmented images. So as you can see, there were cut type of cut out augmentation, brightness augmentation here, and exposure augmentation, and rotation augmentation, and so on. So there were a total of 11,660 images, uh, 11,660 images generated after we augmented the regional image dataset. So for the model selection, as we've mentioned earlier, we chose YOLOv 8 for the model selection. And uh, for the general overview, or for detail, so let's transfer for a larger image of the YOLOv 8 model. You can see here, this is the so here we can zoom in and zoom out of the YOLOv 8 architecture. So we can see more in the YOLOv 8 architecture. So we have here the backbone of the YOLOv 8, in which of course, as you can see, as the P increases, the size of the boxes decreases, because as we know, um, in image classification tasks, or in any task relating to image, the pixels are reduced as the layers increases. So just like any other architectures in regarding image processing, so it also contains layers, convolutional layers also, and C2F modules with additional SPPF layer. So the YOLO V8 is the YOLO, basically the YOLO architecture uses CNN architectures, somehow similar to CNN architecture. So if you're familiar with CNN architectures, uh, you might be familiar with this one. So this YOLOv8 architecture basically contains convolutional layers, C2F module, and SPPF. And this one here contains the details of these layers. So the convolutional layers have the convolutional two-dimension layers, and we have a batch normalization here in the activation function in the last layer, which is CLU, which means it uses the sigmoid function as its activation function, unlike CNN architectures or other architectures which usually uses the ReLU activation function. So we have also here the SPPF, which contains the usually the convolutional layers, and also the max pooling layers, and the concatenation layers, and another convolutional layer. Lastly, we have the C2F module here, which contains the bottleneck layer. So the bottleneck layer here is, if you're familiar with residual networks, so it is somehow similar to the residual block, except that the bottleneck here, except that there's a bottleneck that doesn't have a shortcut here. In residual block, they all have a shortcut there, but here there's a bottleneck, there's a type of bottleneck that doesn't have a shortcut. So this bottleneck is can be found in the C2F module here. So it is also said that YOLO V8 has similar architecture to YOLO V5, which is YOLO V5 is the version before YOLO V8, so they're somehow close. So after YOLO V5, no, I think there's YOLO V7, but uh, the architecture of YOLO V8 is said to be similar to YOLO V5. However, there's the C2F module here. If you see YOLO V5 architecture, the C3 module, YOLO V5 has the C3 module. It is changed into the C2F module here in YOLO V8. So uh, this one, so these are the details of this, and we have here, this contains basically how the architecture works. So in the P3, P4, and P5, this is where the detection happens here in these three layers. So the detection process is repeated so that first it is detected in P3 and then it is improved again and detected again, performs detection again in P4 and then improved again and then performs detection lastly in P5. And then uh, in order to monitor losses also, we use the YOLO V8 uses CLOU, CIOU, and DFL. So CIOU means complete intersection over union, which is an improved version of a distance intersection over union, and the DFL, which so DFL means distribution focal loss. So this means that this too is important in monitoring the class loss, and we have BCE for bounding box loss. CIOU and DFL is used for bounding box, monitoring the bounding box loss, and for the class loss we have BCE. So when I researched DFL, distribution focal loss, is employed by YOLO V8 in order to address class imbalance. So in YOLO V8, it doesn't matter if your uh, data set is imbalanced because there's this function here, DFL, which addresses or which fix that class imbalance loss, which ignores that one. So, having these loss functions will help determine are if the current parameters are the best for the model. Okay, so that was the uh, architecture of the YOLO V8. Basically, hope you understood that explanation. So if not, you can read other research or watch more videos regarding the YOLO V8 architecture. And also, lastly, the training details. So the data set was trained on the YOLO V8 algorithm using RoboFlow, of course, and then transfer learning method was utilized in training the model. So for those who are not familiar with transfer learning is basically you transfer the learning. So we leveraged pre-trained models which were trained. So there were so let's say that it is basically there's a YOLO V8 model which was trained on the Microsoft Coco dataset, and we use the uh we use the features or the features that were learned there by the YOLO V8 that was previously learned by YOLO V8 there, and we transferred it to our current model in order to shorten the training and improve the performance of the model. So that's basically what transfer learning is. You transfer what you previously learned um into the current model so that uh, it basically shortens the training time and also improves the accuracy and performance of the model. So that's all for the methodology part. Now we shall proceed to the results and discussion of the study.
Today, I am Kimberly Faith Alves, and I am now presenting the results and discussions of our paper. So here we can see the graphs for the evaluation metrics that was used to measure the performance of our model. So first, the MAP or mean average precision calculates the average precision value at different recall thresholds. Precision measures how accurately the model predicts positive outcomes by comparing the correctly predicted positive observations to the total number of predicted positive outcomes, while recall tells us how well a model can detect all the relevant outcomes by comparing the number of correctly predicted positive observations to the total number of actual positive outcomes. Here, in this graph, we can see that the model demonstrates a high value of mean average precision and it constantly increases in each epoch, attaining an average of 96.2% and the precision having 92.7% and the recall 91.4%. Here, we can see the detailed summary of the average precision by class of the validation set, this one, and the test set, this one. As we can see, the validation and the test set have an high average precision. So next, we have the graphs for the loss of components during training. So it is important to monitor it for fine-tuning of the model parameters to increase the precision of it detecting an object within an image. So first, the box loss. The box loss compares the predicted and actual position of objects in an image. It helps the model know where and how big the boxes around objects should be. Next, the DFL or distribution focal loss is a method used to improve bounding box regression. Instead of directly predicting exact values for box offsets, it focuses on predicting distributions of offset values, while CLS or class loss measures how well the model can correctly predict the category of objects within the designated areas. So here we can see that all graphs and the losses have a decrease as each epoch. So this would mean that the model, excuse me, this would mean that the model is performing well with the current parameters. We can also see here the graphs of the MAP and the precision and recall. So as we can see, as the epoch increases, the MAP precision and recall also increases, meaning that the training was successful and the model have a high chance of performing well to detect fresh and rotten vegetables. The high MAP may also be because of using a big training data set as suggested by Ultralytics that to train a YOLO model, it needs to have a minimum of 1,500 images. And that's all for our results.
In conclusion, this study addresses a critical need in the agricultural sector by introducing an advanced computer vision model, which is YOLOv8, for automated quality evaluation in agriculture, and also the increasing global population and demand for agricultural product emphasizes the importance of ensuring food safety and quality in the produce sector, in the production sector. The application also of the cutting edge technologies like YOLO V8, partnered with the principles of data driven agriculture, has the potential to revolutionize the industry, promoting sustainability, reducing waste, and ensuring a continuous supply of high quality food products. For the achievements also, we have achieved a mean average precision of 96.2% in training as discussed earlier in the results and discussion, and a promising precision of 92.7% and a recall of 91.4%, which is also comparable to the results of the precision for the validation and the test set. The optimization success. So, uh, we've monitored the loss components in the during training, right? Such as box loss, the distribution focal loss, and the class loss, which indicates uh, these three indicates a successful will indicate a successful optimization of model parameters, and the results reveal that there was a decreasing trend this uh, in this three. So as the there was a decreasing trend uh, in these three as the epochs increases. So this signifies that the model has a strong performance with the current set parameters. In the broader context also of the application, uh, this research this research contributes to the ongoing efforts to enhance operational efficiency and productivity in the agricultural sector. The findings suggest that the YOLOv8 holds promise or holds potential for real-time detection, and also its potential application to sensor technologies. It could further aid into which could further aid the data collection for agricultural development. And we also have the research contribution of this uh, research. So as the agricultural industry continues to grapple with or to uh, continues to tackle the challenges, embracing technological advancements, including AI and computer vision. It This research represents a step towards achieving automated quality evaluation in agriculture, aligning with the global need for sustainable practices, reduced waste, and enhanced food safety. Future research endeavors should focus on refining the model's robustness, addressing specific regional variations, and expanding the dataset for a more comprehensive understanding of the model's behavior in real-world scenario. So that's all for the presentation of the study.